Hi students. Now, now we are going to discuss about that propagation of sound waves. The propagation of sound waves are longitudinal waves. The propagation of sound waves are longitudinal waves. You already know that. So these waves are how they propagate these waves: compression and rarefaction. Okay, then compression, then rarefaction. So like this, the propagation of longitudinal waves are propagate. Okay, so now we are going to discuss about that the speed of light, speed of sound waves. So what is the speed of sound waves? We have to derive the one formula by using that Newton's. That formula is called as a Newton formula. So Newton's, we are going to derive the Newton's formula for speed of sound waves in air. Okay. So the propagation of sound waves are longitudinal waves. You know that these are propagate like this: compression and rarefaction. Okay. The sound waves are moving. So this is the sound waves, like this is the particle. Okay. So these sound waves are moving in air is compression, then rarefaction. Okay. Then again it will be compression and rarefaction. Okay. So when these particles, these air particles, air molecules, these are when compressed. Okay. So these particles are these molecules are when compressed, the pressure will be increases. Pressure increases when that particles or that molecules, that air molecules are rarefaction. Okay, so like this, that that molecules are rarefaction, that is elaborate or elongate. So what happen? This will be having pressure decreases. When the air molecules compressed means, okay, the pressure increases. Pressure increases means what happen? The volume decreases. Pressure increases, volume decreases. That time the temperature is also increases. Okay, this is the one period. Okay, this is the one period. One period means one compression, one rarefaction. Okay, then here pressure decreases, volume, what happen? Volume increases, and what about the temperature? Temperature decreases. Okay, see, I am going to draw one. This is not a longitudinal waves, just you have to understand. So this is the positive and this is the negative. So this will be during compression. Okay, so you can take this part is that during compression the temperature increases. Okay, and this part during the elongation. Okay, so rarefaction, that time the temperature decreases. Okay, so how much heat energy it will be gained? At the same heat energy it will be lost one time period. Okay, so one particular interval of period, how much amount of heat energy increase gain, at the same time that it will be lost their heat energy. Okay, so here the temperature is constant. Temperature is constant. Okay, do you understand? So pressure increases, volume decreases. Okay, here pressure decreases, volume increases. Okay, but temperature is constant. So moreover, one particular period the temperature is constant. So what is the process? So in 8th chapter we can study the process of in isotherm. In heat energy we have learned some process. So thermodynamic process. What are the thermodynamic process? First one isothermal, adiabatic, isobaric and isochoric. There are 4 processes we studied. Did you remember? So in this process here pressure is variable and volume is variable, but temperature is only a constant. What is the name of this process? This name of process is called as an isothermal process. What is the name of process? Pa? Isothermal process. In isothermal process, pressure, volume both are variable and temperature is constant. That means PV equal to constant. Okay, according to ideal case equation, PV equal to nRT. N is a number of moles, that is constant. R is a gas constant, that is also a constant. And T, here isothermal process, T is also a constant. So PV is equal to constant. Okay, now you can differentiate this equation. So you can apply the UV formula. UV is equal to UdV plus VdU. Now you can apply the UV formula. So first, U is a constant, P. Okay, into dV. V is a variable. You can differentiate this variable V. So P dV, then plus. Then again, this is U and this one will V. So V is mean V. Okay, du. U now you can differentiate. So dP is equal to constant. Constant, suppose if you differentiate the constant, that always to be a 0. You can differentiate any constant, it will be always to be a 0. Okay, so P dV plus V dP is equal to 0. Now P dV is equal to minus V dP. Okay, so I can rearrange this equation. P dV equal to minus V dP. Then P is equal to minus V dP by dV. Okay, do you understand, ma? Do you understand this step? P is equal to this, dV is going to right hand side. So in denominator. So P is equal to minus V dP divided by dV. Okay, then next P is equal to here P is equal to minus dP by dV divided by V. So this formula did you studied, ma, in 7th chapter. dP, changing pressure, changing volume divided by axial volume. So this called as an bulk modulus. This called as an isothermal bulk modulus. This will be VL. This is called as an isothermal bulk modulus, that is equal to BL. Okay. Do you understand? Do you understand, ma? So now in velocity of sound, then velocity of sound in air is V is equal to, velocity of sound in air V is equal to, here Vt, because T is a constant, it's a particular constant. So Vt is equal to square root of VL by rho. So this formula we already studied in 7th chapter. Here Bt, because temperature is constant. So Bt divided by rho. Okay. So Bt is equal to, what is the formula? Here P is there. P is equal to minus dP by dV by V. So this is called as a bulk isothermal bulk modulus Bt. So here Vt is equal to square root of Bt by rho. Then next Vt is equal to square root of Bt. You can substitute that pressure P. So P by rho. Vt is equal to P by rho. This is the Newton's formula for speed of sound in air. Okay. So we can substitute that value. We can get the speed of sound in air. Okay. So first pressure. In atmospheric pressure, what is the pressure? In atmospheric pressure is 76 centimeter of mercury. Okay. In atmospheric pressure is 76 centimeter of mercury. So you can calculate that pressure P is equal to H rho G. Okay. So H rho and G. So H value 76 centimeter into 10 power minus 2 into rho value density in air is 13.6 into 10 power 3 into G value 9.8. Then rho value. So this rho value in density in air is 1.293 kilogram per meter cube. 1.293 kilogram per meter cube. These two values you can substitute this formula. We can get Vt is equal to square root of P value is 76 into 10 power minus 2 into 13.6 into 10 power 3 into 9.8. The whole divided by 1.293 into 1.293 kilogram per meter cube. Okay. You can cancel these values. You can get them 280 meter per second. Approximately we can get 280 meter per second. Okay. So theoretically we can calculate the velocity of sound in air is 280 meter per second. But in practically or experimentally, the velocity of sound in air is 332 meter per second. Okay, so much different is there. So in theoretical value, the velocity of sound in air is 280 meter per second. But in experimentally, we can get that value of velocity of sound in air is 332 meter per second. Now you can calculate the percentage error. Okay, percentage of error. You already studied in first lesson. The percentage of error is equal to how much changing error? 332 minus 280 divided by 332 actual error. Okay, so 332. We can get approximately in percentage. We can get approximately 15.6 percentage. 15.6 percentage. Okay, so this value is not good for good value. Okay, 15.6 percentage. So only we can get a very small error means we can accept it. But 15.6 percentage of error means we can't, we could not accept this. Okay, so this formula is failure for proving the speed of sound in air. Okay, do you understand? Okay, thank you.